February 8, 1942. Java, Dutch East Indies. Major Kazuyuki Saito stood before the wreckage scattered across Jakarta airfield, his engineering clipboard forgotten in his hands. The Boeing B-17E Flying Fortress lay partially intact despite its crash landing, abandoned by its American crew just hours before Japanese forces secured the field. Saito had examined dozens of downed aircraft during the China campaigns. He understood airframe stress, engine performance, bomb load calculations, but the numbers his team had just compiled from this captured bomber contradicted everything Japanese naval aviation doctrine assumed about American heavy bomber capabilities. 8 to 10 heavy machine guns distributed across the airframe, over 2,000 miles of operational range with full combat load. These specifications weren't theoretical projections from intelligence estimates. They were measured facts from an aircraft he could touch, dissect, and eventually fly. The Americans cannot possibly field hundreds of aircraft with this level of defensive armament and range, Saito thought, as he walked slowly around the B-17's tail section. The fuel capacity alone suggests production methods we don't possess. Through the bomber's open waist window, morning light illuminated the Browning machine gun still mounted in its flexible position. The gun was half-an-inch caliber, 50 BMG ammunition, each round capable of punching through engine blocks at 600 yards. Japanese bombers carried 7.7mm rifle-caliber weapons for defensive positions. The difference in kinetic energy was 3 to 1. The difference in psychological impact on attacking fighter pilots would prove even greater. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Within 72 hours of securing Java's airfields, Japanese technical intelligence teams located the remains of 15 B-17E bombers scattered across multiple Dutch colonial bases. Some had been deliberately sabotaged by retreating Americans, others had crashed during desperate evacuation flights. But at Mohon Field, Japanese engineers found serial number 41-2471 in surprisingly intact condition. Missing its nose section and engines, yes, but the airframe structure remained whole. The control systems were undamaged. The defensive gun positions could be studied in detail. Torao Saito, an aviation editor from Asahi Press, who toured the captured bases immediately after occupation, documented the discovery in his field notes. The maintenance facilities for the B-17 in Java were excellent for that time and existing conditions. It appeared that Bandung Field was the main maintenance base for the Americans. Here, Japanese technicians from the Gikan began their examination. The Gikan, officially known as the Kokugi, Utsu Kenujo, the Air Technical Research Institute. Based at Tachikawa airfield near Tokyo, this organization employed Japan's most accomplished aircraft designers and aeronautical engineers. When word reached Tokyo that multiple intact B-17 bombers awaited examination in Java, the Gikan dispatched a technical evaluation team immediately. The mission was clear: document every aspect of these aircraft, understand how the Americans achieved such range and firepower, determine whether Japanese industry could match or counter these capabilities. The team faced a formidable restoration challenge. The B-17E represented the most advanced version American forces had deployed to the Pacific theater by February 1942. Its systems were considerably more complex than anything in the Japanese inventory. 4 Wright Cyclone radial engines, each producing 1,200 horsepower, turbochargers feeding compressed air to each cylinder for high altitude. Performance: an electrical system with miles of wiring, hydraulic actuators controlling gun turrets, oxygen distribution for 10 crew members at 30,000 feet, using parts salvaged from multiple damaged B-17s scattered across Java's airfields and pressing captured Allied mechanics into reluctant service, Japanese engineers began the painstaking work of restoring at least 2 B-17S to flying condition. A third aircraft, a B-17D captured at Clark Field in the Philippines during the war's opening days, had already been transported to Japan earlier in the year. The work required months of careful effort. Engineers studied instruction manuals, captured alongside the aircraft, translating technical documentation page by page, learning American engineering practices one system at a time. They measured component tolerances. They traced electrical circuits. They tested hydraulic pressures. They documented bomb release mechanisms, oxygen regulators, and turret rotation systems. By late 1942, Japanese engineers had successfully restored two B-17s to airworthy status. The decision was made to fly them to Japan for comprehensive evaluation at Tachikawa. The flight would require elaborate preparation. The route would take the bombers through Singapore, then northward to Japan, a journey of thousands of miles over territories only recently conquered by Japanese forces. Flight plans were prepared with obsessive attention to detail. Every Japanese air defense unit along the route received advance notification. The description was precise. Two four-engine American bombers, repainted in Japanese markings, would transit your sector on these specific dates at these specific altitudes. Do not engage. Do not fire. Fighter escorts were assigned. A Nakajima L-2D transport, the licensed-built version of the Douglas DC-3, would accompany the bombers as a mothership, ready to guide them if navigation problems developed. Still, mistakes were inevitable when flying enemy aircraft over friendly territory. Anti-aircraft batteries sometimes fired before recognition could be confirmed. Fighter pilots occasionally attacked before escort signals could be transmitted. But in May or June 1943, both B-17Es successfully arrived at Tachikawa airfield near Tokyo, joining the B-17D that had arrived months earlier from the Philippines. Japanese engineers now possessed three examples of America's primary heavy bomber for detailed examination. Major Kazuyuki Saito, the same engineer who had stood in that Java airfield 15 months earlier, headed the evaluation team. His background combined aeronautical engineering education with extensive combat analysis experience. He understood both the theory behind bomber design and the practical realities of aerial warfare. He assembled a team of specialists to conduct the most comprehensive examination ever attempted on an enemy aircraft. Lieutenant Shioyama, Lieutenant Second Class Kurusu and Ohara, Army Assistant Engineer Shimamura, Major Uno and Captain Yagi as test pilots, Army Engineer Kaneo for engine analysis. Every specialist brought unique expertise to the project. Together, they would spend the next year dissecting American heavy bomber technology. The examination began with systematic documentation of the airframe structure. Engineers measured rivet spacing with precision calipers. They recorded panel thickness with micrometers. They documented structural member dimensions, stress points, and load distribution patterns. They photographed everything from multiple angles. They created detailed technical drawings showing internal bracing, bulkhead placement, and control surface attachment methods. What they discovered immediately challenged fundamental assumptions about aircraft manufacturing. The consistency of construction across all three captured aircraft proved remarkable. Rivet holes aligned precisely between different aircraft, suggesting automated drilling equipment. Structural components appeared truly interchangeable, not requiring individual fitting. Panel forming showed identical characteristics across multiple examples, indicating standardized dies and presses rather than handcrafting. This was not artisan construction. This was systematic mass production, using standardized components manufactured to precise tolerances. Japanese aircraft production relied heavily on skilled craftsmen who fitted components individually to each airframe. No two Japanese aircraft were truly identical even within the same production batch. Parts from one aircraft often required careful adjustment before fitting another. Field repairs demanded skilled technicians who could modify replacement parts to match specific aircraft specifications. The American approach appeared fundamentally different. The B-17's construction suggested that any part manufactured to specification would fit any aircraft of the same model without adjustment, without filing, without hand-fitting. This level of standardization required manufacturing precision that Japanese factories had attempted but never fully achieved at production scale. But the defensive armament provided the most striking revelation for engineers who had spent years designing and analyzing bomber aircraft. Major Saito stood in the bomber's waist section, examining the flexible gun mounts. Each position held a Browning M2 machine gun chambered for 50 caliber BMG ammunition. The traverse mechanism allowed wide firing arcs. The mounting hardware was robust, designed for sustained firing under combat stress. The ammunition feed system was reliable, using disintegrating link belts that eliminated jamming from solid belts that earlier systems used. He counted the positions methodically. 2 guns in the nose, operated by bombardier and navigator. 2 guns in the dorsal turret, power operated with 360-degree traverse. 2 guns in the ventral ball turret, also power operated with complete lower hemisphere coverage. 2 guns in the waist positions, 1 port and 1 starboard. 2 guns in the tail turret, providing rear quadrant defense. 1 gun in the radio compartment position. The total reached 9 heavy machine guns on this B-17E model, with some variants carrying 10 or 11 depending on specific configurations. Each gun could fire 750 rounds per minute. Each round weighed approximately 1 3/4 ounces and carried devastating kinetic energy at combat ranges. For comparison, Saito mentally reviewed Japanese bomber armament. The Mitsubishi G3M, which had been Japan's primary land-based bomber until recently, carried 3 7.7mm machine guns, rifle-caliber weapons with limited effective range and penetration. The newer Mitsubishi G4M, that was now entering widespread service, carried 4 7.7mm machine guns plus 120mm cannon in the tail. 5 defensive positions total versus 9 or 10 on the B-17. But the caliber difference was what struck Saito most profoundly. The 50 caliber Browning threw projectiles weighing 3 times as much as Japanese 7.7mm rounds at higher velocities, with far greater range. A 50 caliber round could disable an aircraft engine from 800 yards. It could kill a pilot through armor plate that rifle caliber rounds couldn't penetrate. It could destroy flight control systems with single hits. When attacking a B-17, Japanese fighter pilots would face defensive fire capable of destroying their aircraft before they reached effective firing range with their own weapons. The psychological implications were obvious to any combat veteran. Pilots who see tracer rounds the size of their thumb converging on their aircraft tend to break off attacks prematurely, regardless of mission importance. But range proved equally significant to defensive firepower when Saito's team examined the fuel system. The B-17 carried Tokyo gallons distributed across multiple tanks in the wings and fuselage. With careful fuel management and cruise power settings, the bomber could fly over 3,000 miles. Combat radius with full bomb load exceeded 1,000 miles, meaning targets 2,000 miles from base could be struck and the aircraft could return home. Saito requested the specifications for Japan's G4M Betty bomber for comparison. Maximum range was 2,300 miles under ideal conditions. Combat radius was approximately 900 miles. The American bomber could reach targets 200 miles farther than Japan's newest and most advanced land-based bomber, while carrying comparable or superior bomb loads and vastly superior defensive armament. The strategic implications were staggering for officers who understood operational planning. If one American bomber possessed this combination of range and firepower, and if American industry could produce these bombers in quantity, then Japanese air defenses faced a threat unlike anything encountered before. The Americans could strike from bases beyond the range of Japanese fighter escorts. They could absorb fighter attacks through mass defensive fire. They could sustain operations through attrition that would cripple Japanese bomber forces. By autumn 1943, all 3 captured B-17s were flying regularly from Fusa airfield near Tachikawa. Japanese pilots gained first-hand experience operating the heavy bombers. Test flights documented performance characteristics at various altitudes and configurations. Handling qualities were evaluated through simulated combat maneuvers. The aircraft appeared in Japanese military training films demonstrating tactics for intercepting American heavy bombers. Films showed Kawasaki Ki-43 and Nakajima Ki-44 fighters practicing attack runs against the captured B-17s. These films sometimes featured one of the bombers repainted with American insignia, occasionally escorted by a captured Curtiss P-40 fighter for additional realism. The propaganda value was obvious. Films played in Japanese public theaters, showing Japanese fighters successfully engaging American bombers. Look at our pilots mastering enemy tactics. See how our fighters outmaneuver the American heavies. Trust in our inevitable victory. But what the propaganda films carefully avoided showing was the sobering conclusion Japanese fighter pilots reached after extensive practice intercepts against the captured bombers. Lieutenant Commander Saburo Sakai, one of Japan's highest-scoring fighter aces, flew multiple practice missions against the captured B-17s. His post-engagement reports were brutally honest. Even when we successfully attack the bomber and score hits, the B-17 continues flying. Its defensive firepower forces us to present and see, break off before achieving killing range. Our 20mm cannons lack sufficient ammunition for multiple attack runs. Most troubling, for every B-17 shot down, American factories will produce 5 replacements. This final point haunted Japanese strategic planning more than any tactical consideration. Intelligence estimates suggested Boeing and its subcontractors were producing B-17 bombers at rates exceeding 200 aircraft per month by mid-1943. The numbers seemed impossible, but multiple intelligence sources confirmed the approximate production figures through prisoner interrogations, captured documents, and photo reconnaissance of American manufacturing facilities. If American industry could manufacture such sophisticated bombers in these quantities, while simultaneously building fighters, transports, tanks, ships, and all the other materiel required for global war, what hope did Japan have of matching such industrial output? The question kept staff officers awake at night once they truly understood the numbers. In February 1943, Asahi Press published a comprehensive analysis titled Anatomy of the Enemy's Aircraft. The publication featured extensive coverage of captured Allied aircraft with special attention devoted to the B-17. Photographs showed every major component. Technical drawings illustrated critical systems. Specifications filled page after page with measurements, weights, performance data, and operational parameters. The book became required reading for Japanese aircraft engineers across all manufacturers: Mitsubishi, Nakajima, Kawasaki, Kawanishi. Every company studied the captured B-17, searching for innovations to copy or principles to adapt. The book sold thousands of copies among engineering students and aviation enthusiasts. It represented the most detailed examination of enemy technology ever published during wartime. Mitsubishi engineer Hisanoho Ozawa, designer of the Ki-21 and Ki-67 twin-engine bombers, contributed an article analyzing the B-17 for the May 1942 issue of Koku Asahi, Asahi's prestigious aviation magazine. Ozawa's analysis proved revealing in what it acknowledged directly and what it carefully avoided stating explicitly. He noted that the B-17E represented modifications to a basic design that first flew in 1935, suggesting the aircraft was based on concepts now 8 years old. Martin B-10s and Handley Page Hayfords of the same vintage had already been phased out of frontline service, Ozawa observed, implying the American bomber should be technologically obsolescent. Yet he admitted that continuous improvements had transformed the Fortress into a formidable first-line combat aircraft. The original design had been extremely good, he conceded. American engineers had perfected the subsystems to such a degree that minimal cockpit controls were needed despite the aircraft's size and complexity. What Ozawa's published analysis carefully avoided stating explicitly was the most disturbing conclusion. The B-17's construction methods represented a level of industrial organization that Japanese factories could not match. The aircraft was not superior primarily because of better aerodynamic design or more powerful engines. It was superior because American industry could produce it in quantities that would overwhelm Japanese air defenses through sheer numbers, regardless of tactical effectiveness or loss rates. Another prominent Japanese aviation expert examined the captured bombers and came to similar conclusions. Shizuo Kikuhara, designer of the 4-engine Kawanishi H-8K flying boat, wrote that the American engineers have perfected the subsystems of this bomber to such a degree that a minimum of controls are needed in the cockpit. The simplicity of the cockpit arrangement, considering the plane's size, demonstrated sophisticated systems integration, unknown in Japanese aircraft design. The examination revealed construction details that reinforced these conclusions about American manufacturing philosophy. Wing panels were stamped from dies rather than hand-formed over wooden molds. This required massive hydraulic presses and precision dies costing fortunes to produce initially. But once those dies existed, workers could stamp identical panels by the hundreds per day. Control surfaces showed identical forming characteristics. Every aileron, elevator, and rudder section appeared to have been produced from master tooling rather than individually crafted by skilled sheet metal workers. The main wing spars, critical structural members carrying all flight loads, were machined on automated equipment. Drilling patterns matched exactly across multiple aircraft, indicating jig-based manufacturing rather than hand measurement. The landing gear assembly demonstrated automated precision machining throughout. Main struts were forged components, heat-treated to precise hardness specifications, then machined on automated lathes to final dimensions. Actuating mechanisms consisted of hardened steel components, machined to identical specifications across all three captured aircraft. Japanese intelligence analysts calculated production rates based on these observed manufacturing characteristics, combined with serial number analysis from captured aircraft. If American factories could produce B-17 bombers with this level of precision and consistency, they could produce them rapidly. If parts were truly interchangeable, as the evidence suggested, field maintenance became dramatically simpler, allowing higher operational availability rates. If workers needed less specialized skill because precision was built into the tooling and equipment rather than depending on craftsman expertise, then production could scale up quickly by training new workers rather than requiring years to develop skilled labor forces. The implications extended far beyond simple aircraft count comparisons. Japanese aircraft production faced exactly the opposite situation from American manufacturers. Skilled craftsmen remained in desperately short supply throughout Japanese industry. Training new workers to required skill levels took years of apprenticeship. Increasing production meant finding and training more skilled workers, not simply adding more assembly stations and hiring semi-skilled labor. American strategic bombing would test these different production philosophies directly. When B-29 superfortresses, the B-17's larger and more advanced successor, began appearing over Japan in 1944, each raid destroyed production capacity that could not be quickly replaced. The bombing damaged not just facilities, but the skilled workforce that couldn't be rapidly reconstituted. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By May 1945, American photographic reconnaissance over Tachikawa airfield captured images that puzzled intelligence analysts reviewing the prints in Washington and Pearl Harbor. Clearly visible on the airfield was what appeared to be a new type of Japanese four-engine bomber or transport aircraft. Analysts estimated the mysterious aircraft's wingspan at approximately 104 feet based on shadows and comparison with known reference objects. The unknown aircraft was designated Tachikawa Field 104 based on the estimated wingspan and its location at Japan's primary aircraft testing facility. As weeks passed without additional information emerging from other intelligence sources, speculation grew about Japan's apparent development of a new heavy aircraft despite intensive bombing that had supposedly crippled Japanese aircraft production. Despite intensive analysis of subsequent reconnaissance photographs and careful monitoring of Japanese radio traffic for any mention of new bomber development programs, American intelligence never solved the mystery of the Tachikawa Field 104. None of the analysts who examined those reconnaissance photographs suspected the truth. The mysterious aircraft photographed at Japan's premier testing facility was actually one of their own B-17E flying fortresses, still undergoing evaluation by Japanese engineers more than 3 years after its capture in Java. The actual wingspan of the B-17 measured 103 feet 9 inches, making the American intelligence estimate remarkably accurate, despite the photograph being taken from 20,000 feet altitude. The irony was not lost on Japanese engineers when they learned after the war that American analysts had been tracking their own captured bomber, mistaking it for a new Japanese design. The extensive evaluation of captured B-17s had surprisingly limited direct impact on Japanese bomber design philosophy. Japan attempted to copy the Douglas DC-4E transport as the Nakajima G-5N bomber, but the project failed due to inadequate engines and overly complex systems. Japan's other four-engine land-based bomber, the Nakajima G-8N that entered limited production near the war's end, used more advanced structural designs that gained nothing directly from studying the B-17's airframe engineering. However, there is clear evidence that specific components and systems from the captured B-17s influenced later Japanese aircraft development attempts. Most notable were efforts to perfect turbocharger technology for high-altitude performance. Several advanced Japanese designs, including the Army's Tachikawa Ki-74, Mitsubishi Ki-83, and Nakajima Ki-87, as well as the Navy's G-8N and Mitsubishi J-2M, failed to reach their full performance potential mainly because Japan could not successfully implement reliable turbocharger technology at production scale. The problem was not understanding the technology through examination of captured American equipment. Japanese engineers who studied the B-17's turbocharger installations understood perfectly well how the systems worked in theory. They could document the airflow patterns. They could measure boost pressures. They could trace control systems. Understanding was not the limitation. The problem was manufacturing. Turbochargers required high-temperature alloys capable of withstanding exhaust gas temperatures exceeding 1,000 degrees Fahrenheit for hours without warping or cracking. They required precision manufacturing of turbine wheels spinning at tens of thousands of revolutions per minute with tolerances measured in thousandths of an inch. They required sophisticated bearings capable of operating at extreme temperatures while maintaining precise clearances. Japanese industry understood what was required. Japanese engineers could design appropriate systems, but Japanese factories could not consistently produce the components to required specifications in meaningful quantities. Even when experimental turbocharger units were successfully built and tested, they proved unreliable in service. Turbine wheels cracked, bearings seized, housing warped from thermal stress. The same manufacturing limitations that prevented mass production of truly standardized B-17 components prevented development of advanced engine technologies that required even tighter tolerances. By 1944, the cumulative evidence from examining captured American aircraft had led thoughtful Japanese engineers and strategic planners to sobering conclusions about relative industrial capabilities that could no longer be dismissed as pessimism or defeatism. These were mathematical facts. American aircraft production reached 96,000 aircraft in 1944 across all types. Japan struggled to produce 28,000 aircraft in the same period despite maximum mobilization efforts. But the disparity in raw numbers dramatically understated the real capability gap. American aircraft consisted of thousands of precisely manufactured interchangeable parts. They could be maintained by mechanics with basic technical training using standardized replacement components shipped from central supply depots. They could be repaired quickly in field conditions and returned to operational service within days or even hours. Damaged aircraft could be rebuilt using components from multiple airframes. Japanese aircraft remained essentially craftsman-built machines requiring skilled technicians for proper maintenance. They needed specialized parts manufactured to match specific airframes for many repairs. They demanded constant adjustment and hand-fitting to remain operational. Each Japanese aircraft represented greater maintenance burden and lower operational availability compared to equivalent American types, meaning that even identical production numbers would still favor American forces through higher sortie rates. The production system that enabled American output was visible throughout the captured B-17's construction for engineers trained to recognize manufacturing signatures. Boeing's Plant 2 in Seattle had produced 6,981 B-17s across all variants by the time production ended in April 1945. At peak production in 1944, 16 complete B-17s rolled off the Seattle assembly line every single day. 16 aircraft, one every 90 minutes around the clock. Douglas Aircraft in Long Beach, California, produced 3,000 B-17s between July 1942 and July 1945. Lockheed Vega in Burbank built 2,750 B-17s between August 1942 and August 1945. Total B-17 production reached 12,731 aircraft from all, 3 manufacturers combined. Japanese engineers examining captured B-17s in 1943 and 1944 had no access to these precise production statistics. American security prevented such information from appearing in captured documents or prisoner interrogations, but engineers could calculate approximate production rates based on observed serial numbers and construction date codes documented in the captured aircraft. The mathematics proved devastating. If American factories could build B-17s with such precision and consistency as the captured examples demonstrated, they could build them rapidly in massive numbers. If they could build heavy bombers this quickly, their production of fighters and other aircraft types must be proportionally greater. Simple arithmetic suggested Japan had entered a war of industrial attrition against an opponent with perhaps 10 or even 20 times its manufacturing capacity across all categories. The strategic bombing campaign against Japan's aircraft industry, which intensified throughout 1944, destroyed any remaining hope for somehow matching American production through improved efficiency or extended work hours. Boeing B-29 Superfortresses, the B-17's larger and far more capable successor, appeared over Japan in formations that Japanese air defenses could not effectively stop despite desperate efforts. Each raid destroyed production capacity that could not be replaced due to shortages of machine tools, raw materials, electrical power, and skilled workers. The Nakajima plant at Musashino, producing engines for multiple aircraft types. The Mitsubishi facilities at Nagoya, Japan's largest aircraft manufacturing center. The Kawasaki factories producing army bombers and fighters. All suffered severe damage from precision bombing attacks that systematically dismantled Japanese industrial capacity. An earthquake struck central Japan in January 1945, compounding the damage from American bombing by destroying much of Mitsubishi's supplier network. The combination of strategic bombing and natural disaster effectively collapsed Japanese aircraft production. Monthly output had peaked at over 2,500 airframes in May 1944. By early 1945, production had fallen to barely 1,500 aircraft per month, despite maximum effort. The decline continued through the war's final months as raw material shortages, power outages, and worker absenteeism combined with bomb damage. After Japan's surrender in August 1945, the United States Strategic Bombing Survey conducted comprehensive examinations of Japanese war production capabilities. Teams of American engineers toured Japanese aircraft factories, documenting production methods, assessing industrial capabilities, and determining why Japanese output had fallen so far short of initial American intelligence estimates from 1941. What they found confirmed the conclusions that perceptive Japanese engineers had reached years earlier through examining captured B-17s. Japanese aircraft production relied heavily on skilled manual labor throughout the manufacturing process. Standardization remained limited to basic components. True interchangeability of parts remained more aspiration than reality across much of the industry, despite official policy requiring it. Subcontracting networks provided components, but quality control and dimensional consistency proved problematic when parts from different suppliers were assembled into complete aircraft. American engineers touring the Mitsubishi facilities at Nagoya observed skilled craftsmen hand-forming aluminum panels that would have been die-stamped in American factories using hydraulic presses. Manual riveting predominated where American factories used automated riveting machines. Individual fitting and adjustment of parts were common practices where American factories used precision-manufactured interchangeable components. The survey's final report concluded that Japanese aircraft factories had been organized appropriately for producing hundreds of aircraft as specialty manufactures. American factories had been organized systematically for producing hundreds of thousands of aircraft as industrial commodities. No amount of worker determination, engineer cleverness, or management pressure could overcome that fundamental disparity in industrial organization and manufacturing philosophy. The captured B-17s examined so carefully at Tachikawa from 1943 through 1945 were destroyed in the war's final months, either by American bombing raids on Japanese airfields or by Japanese authorities, eliminating evidence before occupation forces arrived. The physical aircraft are gone, but the lessons those captured bombers taught survived in the minds of Japanese engineers who had studied them so carefully and systematically. In the decades following the war, Japanese industry underwent a transformation more comprehensive and fundamental than anything attempted during wartime, when production pressures prevented systematic reorganization. Engineers who had examined American aircraft and carefully documented American production methods brought those lessons directly to Japan's post-war industrial reconstruction. They understood from first-hand study that matching American industrial capability required not just copying American products, but implementing American production systems and manufacturing philosophies. The transformation required approximately 20 years of sustained effort. Japanese factories that had relied on skilled craftsmen for aircraft production reorganized around precision machinery and automated processes for post-war manufacturing. Industries that had valued individual craftsmanship above all else learned to value systematic efficiency and process control. Manufacturing operations that had been organized as collections of skilled workers evolved into integrated production systems where quality came from process design rather than worker skill alone. By the mid-1960s, Japanese factories were producing automobiles and electronics using automated production methods fully comparable to American factories and in some categories exceeding American efficiency. By the 1970s, Japanese manufacturers had refined those methods further, developing production systems like Toyota's just-in-time manufacturing that actually improved on American mass production techniques through systematic waste elimination. The skilled craftsmen remained valued in Japanese industry throughout this transformation, but their role fundamentally changed. Instead of individually crafting products through manual skill, they designed production systems and tooling that enabled less skilled workers to produce precisely manufactured products at industrial scale. That precision that had once come from the craftsman's trained hand and experienced eye now came from the precision of the tooling, equipment, and process controls. Companies like Toyota, Sony, and Honda became global industrial leaders by combining traditional Japanese attention to detail with American systematic production methods studied from captured equipment decades earlier. The quality that Japanese products became famous for worldwide resulted from production systems carefully designed to build quality into the manufacturing process itself, rather than relying on skilled workers to individually craft quality products through manual expertise. Ironically, in the 1980s, when American manufacturers faced intense competition from Japanese imports, American engineers toured Japanese factories to learn modern efficiency techniques. The irony was not lost on those familiar with the history. Japanese engineers had learned systematic mass production by examining captured American police and bombers in 1943. American engineers were now learning refined production methods from Japanese factories in 1983. The wheel had come full circle. The story of Japanese engineers examining captured B-17 bombers became a standard case study in Japanese engineering schools and manufacturing programs. It illustrated perfectly how examining an opponent's products could reveal fundamental principles of industrial organization that transcended specific product design. It demonstrated that competitive success required understanding not just what competitors produced, but how they produced it. It showed that the principles of production ultimately determined outcomes of industrial competitions, more than design excellence or worker dedication. The captured B-17s had taught Japanese engineers during wartime that modern industrial warfare was won not by superior craftsmanship, but by superior production systems, not by building better individual aircraft, but by building adequate aircraft in overwhelming numbers that enemy forces could not counter through tactical excellence alone. Not by skilled workers operating manually, but by systematic processes that enabled less skilled workers to produce precisely manufactured products rapidly and consistently. Those lessons, learned through careful examination of enemy equipment during desperate wartime conditions, became the foundation for Japan's post-war industrial success story. The transformation of Japanese manufacturing from craftsman-based production to systematic mass production represented the final vindication of the principles embodied in those captured B-17s examined so carefully at Tachikawa 7 decades ago. The engineers who had measured rivets and documented production methods in 1943 and 1944 became the architects of Japan's industrial rebirth in the 1950s and 60s. They had learned by examining aluminum and machinery that modern industry belonged not to those with the most skilled workers, but to those with the most effective production systems capable of consistent output at scale. In manufacturing engineering courses today throughout universities worldwide, the story serves as a powerful case study in competitive analysis. It demonstrates that understanding an opponent's methods matters more than copying their designs. It shows that the principles of production ultimately determine the outcomes of industrial competitions. It illustrates that examining how competitors manufacture products reveals insights impossible to gain from studying the products themselves. The Boeing B-17 Flying Fortress dropped 640,000 tons of bombs during World War II. It earned its reputation as one of history's most effective strategic heavy bombers through combat operations in every theater of the global conflict. But perhaps the captured bomber's most important contribution to history was not the missions American crews flew in combat, but rather the lessons Japanese engineers learned when they examined captured examples with systematic thoroughness. Those engineers discovered that American industrial power came not from superior raw materials or better basic designs, but from superior organization of the manufacturing process itself. They learned that standardization, precision tooling, interchangeable parts, and systematic production methods could achieve what skilled craftsmanship alone could never accomplish. The ability to produce complex machines rapidly and in quantities limited only by available resources and industrial capacity. The captured B-17s examined at Tachikawa are gone, destroyed more than 70 years ago in the final chaos of a lost war, but the lessons they taught transformed Japanese industry and influenced manufacturing practices worldwide for generations. Engineers and manufacturers globally learned from Japan's example that mass production and quality were not opposites but complementary aspects of properly organized industrial systems. The story that began in February 1942 on a muddy Java airfield with a damaged Boeing B-17E awaiting capture by advancing Japanese forces ended decades later, with Japan and America as close partners and allies in advancing manufacturing technology and industrial cooperation. The examination of those captured bombers had taught Japanese engineers that their wartime defeat was inevitable given the industrial disparity. More importantly, it taught them why defeat was inevitable, and in understanding why, they learned exactly how to ensure that industrial inadequacy would never again limit Japan's capabilities or constrain its future. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.